Thank you all for coming and welcome. Well, a while ago I was invited to do a talk here. So since this is a very knowledgeable crowd, I started thinking what to talk about. So the first idea, of course, was blockchain, because everything's about blockchain now. And with all the real and fake news and renders coming out that are becoming more realistic by like every day, we need some kind of proof on that. But I figured let's do that on another conference. So maybe AI could be another cool topic, but that will only trigger these like machine rising discussions. And I'm going to be talking about machine learning, deep learning anyway, so nothing about AI in specific. So maybe biocomputing could be a cool topic, because at some point we're going to actually use our neurons instead of CPU, GPU. But then I thought, you know what, screw it, let's just stick with what I know. Let's talk about depth sensors, and let's talk about using XR equipment in production. So a quick little introduction about myself. My name is Jasper Brekelmans. As you might hear from my accent, I'm not from the US, I'm from Amsterdam in Europe, in the Netherlands. There's more people there, apparently. You may also know me under my name as Brekel, because under that name I've been toying around and working with all these types of depth sensors. So there's a Connect 1 and 2 at the top, it's an Orbeck Astra at the bottom left, a Leap Motion and some Intel Real sensors, but we're going to talk more in depth about those. What my background is this. So this is professional motion capture. So I'm sure a lot of you have seen this in all the big making-ofs of movies. Or this is a Vicon system. So essentially, we stick these retroreflective markers on, well, basically anything, but we prefer characters or actors, I should say. So we stick them on. We have about 20 or 30 cameras that are looking at them at the same time. And then we can do real-time triangulation, build a skeleton, retarget the skeleton to a character, and then, as you can see, we can display that in real time. So the actor can actually look at that, the director can also look at that. And essentially, we can do this type of virtual production where we do camera switching, and we can actually all look at the results in real time, come up with blocking, etc. So here's an example of data. So as you can see, it's full 360. We can do multiple characters. We can place the camera anywhere where we like. We can do like stunt work. We can even do fingers, etc. And we usually combine that with facial capture. So in this case, this was shot with a Dynamics helm. So there's a helmet with a little camera on top, but actually on the front, so it's hovering in front of the actor. We can do things with 2 cameras, 4 cameras to do like proper depth on that. And then we use machine learning, and we build a tracker. I'm not sure if you can see it, but on the left image, you see all these dots on my face. So basically, we train a tracker specifically for an actor. In this case, this was a test thing for me. Then we do a tracking, which is usually something like 60 or 120 frames a second, so that we capture all the little nuances. And then again, we retarget the whole thing so that we can keep different proportions in the face into account, and then retarget to a character so that it fits on a new face. Now, one quick example of a project that we did for that was Sweetie for Terre des Hommes. It's a pretty heavy topic because it's about catching predators of webcam child sex tourism, which unfortunately is a thing on the internet these days. And Terre des Hommes, a couple of years ago, they discovered that the threshold for this is getting lower and lower, so the entry point was getting getting easy to get into, unfortunately. So what we did with them is we developed this virtual girl. Now what I'm showing you here is just marketing material. So we developed this girl. It was actually an item on CNN, I think. That's where it's coming from. And we could use the girl in a chat room, online chat room. So we delivered software for this and delivered it to authorities all over the world. And they're actually combining this with data from Facebook, Twitter, etc. That data that people already share, and that's how they can actually track down these people. Legislation has been changed all around the world. There's been several arrests, and this has actually changed a lot of opinions and laws. And as you can imagine, I can only show the marketing material because the rest of this is pretty secret and pretty sensitive. But at least this is an example of how we use these type of high-end technologies. Now, let's talk about depth sensors. I think A lot of you probably know what depth sensors are, but let's do a quick level set. We all know what a video sensor is. So essentially, we get the red, the green, and the blue pixel, and we get a video image out of that. Now, a depth sensor adds additional information. You can see there on the left, I have a colorization where every pixel that is like a white pixel is closer to the camera, and a dark pixel is further away. And as you can see, there's some noise in the background. But essentially, when we do that, we can generate a point cloud, and we can map the video data to that. Some examples of that, here's an application that allows you to do recordings of that. So here's a live 3D point cloud from, in this case, a Kinect 2 sensor. And it can be recorded and then exported to popular 3D formats like Alembic and like general video and texture formats. So you can use it in like pretty much any 3D application. You can also use it in Unreal and Unity for real-time applications, for example. But I'll show you some projects for that later on. I wanted to explain a little bit of theory. So I want to dive into the different types of depth sensors there are. So the first one is a structured light sensor. Now, the way they work is actually fairly easy if we break it down. So if we look here on the left, we have a projected pattern. So in this case, just for an example, I'm choosing a line. And if we project that line into the scene and look at it from a different viewpoint, then we can see that the line gets split up and it gets distorted by the cylinder. And if a sensor does that, it usually doesn't do a line, but it uses more something like this. So it looks like a pseudo-random pattern. This is actually one from Kinect version 1, which just projected to a flat wall. That is embedded in the sensor. So with the sensor calibration, it can then, if it projects into a room, it can then figure out per cluster how things are deformed, and that's how it figures out the depth sensor data. Excuse me. There's actually other patterns that we can use. So here's an industrial application. It's using, it's more like a sine wave type thing that's actually traveling, and it does different resolutions. So that's how they use it to do like part inspection, for example. There's also been examples of research that has done these type of colored lines so that they can do more tricks, and they need fewer frames to get the depth information out of it. Some examples of sensors that are using this. Top left, we see the Kinect 1, which was done for the Xbox 360 by Microsoft. The bottom left, we see an Orbeck Astra sensor. In the middle, iPhone X. Actually, that little notch there at the top that does the facial login, the facial recognition. That's actually the same sensor, or at least a derivative of the same sensor as in the Kinect 1, because Apple bought the company behind that chip a couple of years ago. It is a much lower powered version, so it doesn't have as high of a frame rate, not as much detail as a Kinect sensor does. And there on the right, you can see a industrial type scanner. So those are generally used to scan in, to do very high resolution scans of static objects by moving the scanner around them. The second principle we can use for depth sensing is time of flight. Now, actually, if we go back to nature, we know this as sonar. So some animals, they send out like a ping signal, and then they listen to the echoes of the room, or they listen to echoes from a prey, for example, and they can figure out what to do and what the surroundings look like. We as humans have adopted this in submarines, so it's the same principle. But besides audio, we can also do this with light. And again, a little diagram. So the idea is we send out a very quick flash of light that gets bounced around in the scene. If we look at that from a different sensor, then we can essentially figure out, because every object is very close by, will reflect the light back earlier than objects that are further away. Now, in reality, this is a little bit more complex because we're dealing with speed of light here. So usually these things are modulated and time shifted, but let's not go into that because that could be a whole talk. The basic idea is objects that are close by will reflect quicker than objects that are further away. So some sensors that use this. On the left, you can see a Kinect 2, which was the sensor for the Xbox One controller. Then in the middle, we have a professional LiDAR scanner. So the idea here is there's usually a rotating laser in that. Then you walk around with the stick to scan like huge rooms like this, for example. which is used a lot of times in visual effects production to scan sets, for example. Then on the right, we have a Microsoft Hololens, which actually has a similar sensor to a Kinect 2, but again, very low power, very small, which is in front of the top sensor pack we see there. A little bit more about the HoloLens at the end of this talk. And the last type we have is stereo. Now, stereo is basically, we have two cameras, we calibrate them, we know where they are in relation to each other. So it's the same idea if you stick your thumb out and you look at it with your left eye, your right eye, you can see your thumb switching about. Now, if we look a bit closer, oops, let's use a more friendly picture. Here we have a dog with like a left and a right eye. And the first step we do is we try to identify points. Now, these type of feature points, the idea behind them, you can do it with different algorithms, but the idea behind them is that those points should be in the same spot on the physical model, even if the camera is changing. Now, as you can see, there's a lot of noise. There's a lot of points that don't match. So usually the second step is bundle adjustment, where we try to figure out which points in the left image match the one in the right. And here's some examples from the automotive industry. So as you can see, it delivers pretty noisy images. So on the streets, for example, or in the sky, there's hardly any texture, which results in these black spots, which is a general issue with stereo. The advantage, though, is that all you need here is two cameras, so you can stick them on a car and have these huge depth ranges that you can measure with them. Some examples of that are human eyes. Not so sure about Bill Murray's eyes, but there on the left we have a leap motion sensor, which hopefully a lot of you guys have strapped onto VR headsets, which is specifically meant for doing tracking on fingers. And there on the right we have a more typical photogrammetry setup, which is used for visual effects. So the idea here is that we have not just two cameras, but we have sets, like a multi-stereo setup. And the idea is we have a person in the middle so that we can get like one image of all these cameras at the same time and then do the stereo compensation for that to get a very high resolution image out of it. And the last one I wanted to quickly mention is a hybrid sensor. The whole reason for this is that Intel released these. These are the Intel RealSense ones. And essentially they're a stereo sensor, but they have an active infrared emitter in them. Now, I'm not sure if this is visible here on the screen, but on the bottom left, you see an image of the sensor in passive mode. And on the top left, you might be able to see that there's a dot pattern on the floor. And if we look at the corresponding depth image, we can see that can actually fill in quite a few of the holes that are in the image. Here's another view from the side. You can see on the left there's the passive image, on the right is the one with the active emitter enabled. And you can see it filters out quite a lot of the noise as well as some of the holes. So I think that's enough theory for now. Let's actually look at some examples. So here's a project called Asphyxia, which was done a couple of years ago with two Kinect 2 sensors. The group had a dancer, and they put a sensor on the front and on the back. They recorded this and then took it through a 3D application called Houdini to do this type of procedural animations on it. I think Microsoft also picked this up for one of the Super Bowl campaigns for the Kinect sensor. Another one, this was recently launched on Kickstarter and actually in full production at the moment. They're using it more as a volumetric video type of production. So they're actually doing recordings and then playing it back in the Unreal Engine. And the idea here is that since it's volumetric, you can actually get more up close and you can get more intimate with the people that they're interviewing. There's another one by realityvirtual.co. Some of you may know them. Again, this is done in Unreal. Here they're using a mesh, and they're trying to do reprojections of patterns, like light patterns on them. So they have this aureolus effect, so they can do relighting and try to integrate it with the background in this case. And again, this is meant for VR, so you can actually walk around it and look at it from different viewpoints. This is a test movie. I'm not sure what they exactly did with the final result for that. Essentially, they're scanning, a 3D scanning company, so usually they combine this with photogrammetry backgrounds as well. Then here's another one, it's a longer thing by a group in Germany. They focus on theater-based performances and recording and playing them back in VR. So here's an example for archaeology. They use 2 sensors to record this from different sides, and then this elaborate point cloud visualization, which gives you a bit of a more abstract view on this type of motion. Now, essentially, these type of recordings are pretty much the same as any video recording. So you have your sets, you have your actors, and instead of recording with a video camera, you're just recording with a sensor and a computer, or multiple, which means that you can do a lot of the same tricks, like blowing wind up the hair, for example. They're actually using Unity for this. So here's a test setup with some playback of that. So the playback is usually streamed from disk, so you can handle large files, but then you can still walk around it with the headset. Here's an example of a multi-sensor shoot. So you can probably make out in the image to connect 2 sensors. The idea is that if we place them in a circle, all pointing inwards, then you can actually see the back of the person and fill in all the holes that a single sensor from the front couldn't see, for example. You can actually, on the monitor, spot that they're using different colors. So it's usually done in production to figure out which point belongs to which sensor. But they're all recording color as well, of course. This is an example of a little diorama thing they did. So there was a photogrammetry shoot of the environment. And then it's literally placed on a little table. You can stick your head into it and then see these ghostly figures that are dancing in the background in this case. They've been experimenting with a lot of different visualization methods, so including pixelization, different shaders. They even did tests where they had the actors in black clothing, this one, so that you essentially end up with a floating head, because some type of clothing can be very difficult for a depth sensor to pick up. You can actually do creative things with that. And the cool thing about a lot of these VR playbacks is that you can look at them from any side. You can actually exploit that in certain situations. And the funny thing is also that people react very differently to it, especially if they come close to you, of course. So some people are very passive about it, some are more active, and you have some people that are doing this. So you can have a lot of fun with that. But besides point clouds, we can go much further. So one of the most used things is body tracking. So if we have a look at that, the idea is basically we have a point cloud, and if we identify in the depth image which pixels belong to a human, so in this case on the top left you can see all the blue pixels are identified as a human body. And then we can look further and we can look deeper into recognizing the body parts. And then once we figure out what those are, we can build a skeleton out of that. And again, that can be exported to 3D file formats that are pretty standard, like FBX and even like the older style BVHs. And then you can get it into your 3D application, do retargeting, use it for a 3D character, for example. And this can be recorded, but it can also be live. Here's an example of a multi-sensor body tracking. This is actually an application that's still in beta, so you do see a rudimentary form of this, but it is actually available for testing. Now the idea is we have 5 sensors in this case, but we first need to know where every sensor is in relation to each other. And with this live calibration, we can actually use the data from the sensor itself to figure out where everything is in relation. For example, we can use the point cloud data as well as some of the body data, and then do a live calibration. Once we have that, we can do a fusion of all the skeletal data, so that we fill in blanks. This is actually an old solve, so you might see some problems with the hips that have been solved by now. This is also deliberately a bad setup, so all the sensors are on the front, but it still delivers enough data so that you can do things like turning around, for example, like you can see here. And essentially, you can have different sensors from different brands, different sensors from different network computers, or all stuff into a single giant computer with enough USB power. Now, this body tracking has actually been made possible by Microsoft a couple of years ago. So I want to do a quick dive into the paper and explain how this thing works. Essentially, what was done is they created this huge synthetic library of images. Here you can see these are the labeled images that are showing the body parts. Now, these were generated essentially by a character rig with different body proportions and loads of different poses. Like you have to think about like hundreds of thousands or even millions of different poses. And because they had depth images and these synthetic labels with that, they actually could train a machine learning algorithm. I think it was a random decision forest actually. And after it's been trained, which can take a lot, like even a couple of days on the big farm, you can feed it with live depth images. So there at the bottom left, you can see the live depth feed of a sensor. And on the bottom right, you can see the result from the trained trained machine learning algorithm where it's identifying all these pixels. Now you can see it's a little bit noisy, but actually the results are really pretty good. And this runs in real time. Then the last step that needs to be done is we need to find out how the clusters relate to where the joints are. Now you can't really stick a joint on top of the depth sensor data, because then the joint ends up like at the front of the body and you actually want it inside. So with the same learning data, they also taught a system that can actually figure out how far the joint has to be pushed back. Now, that was all a couple of years ago by Microsoft, but we've actually gone a lot further. So here's a project using deep learning. OpenPose is actually available on GitHub for non-commercial use. This uses regular video images, so there's no need for depth images anymore, which means you can run it on like YouTube clips like this. It doesn't fully run real time. This is actually an example on a 1080 Ti. And runs at about 12 frames a second or so. I think they've upped the speed a little bit by now. And the disadvantage is that this is also just in 2D. Now, Carnegie Mellon, where this originated from, has gone a bit further, so they've also trained finger tracking models as well as facial models. This is definitely not real-time anymore, but it shows the potential of doing at least 2D human pose detection on purely RGB images. There's other projects like DensePose that are trying to do it in 3D. So they actually do a more of a UV-based type of lookup, where they can actually get a little bit more information out of this. Again, it's available on GitHub for non-commercial use. So the point here is that we're getting more and more out of deep learning at the moment, which might actually mean that we can get more out of RGB images. And we may not have to rely on depth images all the time. Quickly, we can also do face tracking. The idea here is once we do body tracking, we can search a bit further into the facial area and then identify key points on that, which we can then solve into expressions. So here's an example of 20 different expressions. You also get a position rotation out of the head. And again, that can either be live streamed, but also be recorded in FBX format so that you can use it on pretty much any 3D character or any 3D application. Anyway, I think that's enough for depth sensors, because we have some other cool things to talk about. But a quick roundup on the advantages and disadvantages. They're very inexpensive. I mean, these are consumer sensors, all in the $100, $150 range. They require no calibration, so you can literally push it on a desk and hit record, and that's it. Now, they are also pretty noisy and fairly low resolution. The depth is usually in the range of an SD, like standard definition type. And these sensors are primarily designed for developers, so you do need some coding knowledge and an SDK in order to get data out of it. But then again, there's applications that solve that already. And this actually opens up a lot of doors for indie developers. I have a lot of clients that are like a 2D game developer studio somewhere that are actually trying to get into motion capture, and they can actually do a lot of stuff with simple stuff with these type of sensors. And once they grow further, they can always hire a high-end motion capture company and get further into that. And at the same time, like pretty much every visual effects company in the world also has these type of sensors, but they use it more for prototyping. So they have it on an animator's desk. They can hit record, get some quick animation data in, so they can test things out. For example, some friends of mine have a studio that does character design, and usually when a client comes in for approval process, they let the client live drive a character, which really smooths out the approval process usually. I also, in the last part of the talk, I want to talk a little bit about VR and AR, because I mean, that's obviously the topic here in this conference. Now, quick level set again, I think we all know exactly what VR is. It's an HMD, and it generates VR mouth. And here are some examples of VR mouth. As you can see, it's not connected to any type of brand, also not connected to any type of age. So, I think most of you have also read articles like this. So where the last Ready Player One movie used a lot of this technology in production. I'm actually going to show you the little standard clip from YouTube. As a disclaimer, I didn't work on this. I'm just showing you this to drive a point home. And the point is that when we're doing productions on high-end visual effects or even low-end visual effects movies, we're working with all these three-dimensional data. And usually we're working on it and discussing it on a big screen. So it's a very natural process to actually put on a VR headset because all of these assets are in 3D already. And it opens up new possibilities, especially for these large sets where we have to figure out camera motions, where we have to figure out if the characters fit in there, do blocking. So the more we can do in 3D, the more it actually helps these type of productions. So I think here you see some shots of where they actually start doing camera planning for it. And also, these productions, they already heavily rely on giant studio setups where they do virtual character production, they do live performance capture, but they're all being done in studios like this. So it's essentially a giant empty room with lots of cameras and lots of technicians running around. And we're relying on the actors to have a vision on what they're actually playing. So the more that they can be, the more info they can be given in the form of visual images, the better they can do their performance. Because if they know what set they're working in, if they know what the character looks like, if they know what the other characters look like, it just helps the performance to be more in context, instead of just relying on a few printed out images or screens and walking in this big, giant empty room, for example. We can also turn things around, and for production we can have a look on what these sensors actually give us. So here's an example by Oliver Kraylos that did tracking for the Oculus Rift. I think this is an older Oculus, but the idea is the same. So the way it works is there's all these flashing infrared lights. They all flash in a certain sequence so that we can figure out which one is which. And then the infrared camera looks at that, and essentially, since it knows where every sensor is, it can then fairly easily and very quickly figure out the pose of the object. So that's how it does position rotation tracking for that, which is actually, again, a technique that came out of high-end professional motion capture. I think Face Space is actually on the floor downstairs, so using also a similar type of flashing LED technique, I think. If we look at the Microsoft headsets, they work on a different technique. Essentially, they do slam tracking. So they have multiple, usually two cameras that are facing outwards. And again, they're looking at feature points and then comparing those to a point cloud they've already seen from previous images. That's how they can figure out where the position rotation is of a camera. And again, as you can see, it's very, very quick and delivers very high-end quality that we can actually maybe even try to use for production. And lastly, we have the HTC Vive, which from my experiments and measurements is still the highest quality tracking device, at least. Now, the way that works is different. In the base stations, there are two different lasers. Well, actually, on the new one, I think it's one laser, but the idea here is we have a vertical sweep and a horizontal sweep. And in the controllers and in the headsets are all these little photosensitive diodes. And the idea is that sensors on the left may not receive the sweep at the same time as sensors on the right. So that's how a chip inside the controller and inside the headset can do calculations on its position and rotation. Now, we actually did some tests. So what you see here is we have a high-end marker-based system called a Vicon, and you can see those in the blue dots. And we have a previous generation HTC Vive, so the non-pro version, here displayed in yellow or orange. And we overlap all of them, and we do a recording at the same time. Now, we figured it out that the data that we get is very high frame rate, actually very little noise, but there was one peculiar thing. If you look at the head, for example, you see that both of them are pretty well aligned. But then as soon as I turn around, then there's a warp in the Vive data, which we could confirm on another system setup as well, but we couldn't really figure out what it was coming from. So it might have been some calibration problem or some interference. But the takeaway here is that this data is very, very accurate. It's very close to a system that costs a couple $100,000. And again, we can record all this stuff. So again, Rift, Vive, like basically anything that works through OpenVR. We can record to FBX data. And again, FBX data we can get into, here's Maya, for example, but it can be imported in any 3D app. And then we can use it to drive models. Also with HTC Vive, we have these separate tracker pods. So you can put them on your feet, put them on your hips, then use an IK system, inverse kinematic system, to build a skeleton, for example. But I've also talked to a lot of people that are sticking these on cameras, different props, like all these types of different creative uses. And another funny thing you can do, because it's OpenVR, you can actually run this while a game is running. So you can do this for playtesting, for example. The user just sees the game as they normally do. And then in the background on the desktop machine or the laptop, the software is recording all of this, including video and audio. So you can quickly do playtesting. There's also some medical uses for this, for example, where they put people in VR and then want to record as much data in context. Now, lastly, I want to touch upon AR. I'm sure you all know what a Hololens is. Basically, it's a Windows 10 computer stuck to your head with lots of cool sensors and a transparent visor. So again, this has a depth sensor in there and some tracking sensors. And the idea here is that they're completely aware of the environment. So it uses something called spatial mapping with the depth sensor, and that allows you to place characters in your living room or on, and they can walk all over your couch and jump everywhere. Also, if they're behind your table, for example, they'll be occluded by the data collected from the table. There's examples here on the show floor where you can actually try this. Now, since I've done a lot of stuff with Kinect, I was able to buy a HoloLens about 2 years ago or so. And this is one of the first things I tried. So this is my actual living room with some holograms that I like. And the idea here is I had a laptop there on the table with one of my favorite 3D animation applications called Motion Builder. And I developed a quick application in Unity, which is run on the HoloLens. And the idea here is that I have the same model in my living room as I see on the laptop, and I have a live link. So basically, I can place this anywhere I want. And the wireframe shows that the HoloLens figured out what my apartment looks like. And when I do something on the laptop, it's reflected on the same model in my living room. So in this case, it's an inverse kinematics rig. But since I'm this motion capture dude, I have lots of motion capture files laying around, so I can do a playback on that. Again, this is standard animation software that I'm used to. So I played that back, then there's the live link, and I see the exact same thing happening on the robot. Now in this case, the robot is actually life size, so it's about the same size as me. So I can walk around and inspect it from different areas, which means that I sometimes have to replace so that they have a little bit more room. But I can get really up close and personal, so I can actually dive into the little details and see all the different details of the model and the motion. HoloLens also supports voice commands, so it can do things like, say, make it smaller or make it bigger to do 50% or 200, for example. And I can do these gestures. So in this case, I built in this rotational thing, so I can pick up the little cylinder there and then rotate it around. Now, the idea is, I have this really nice animation application on my 2D desktop, but we as 3D artists, we're always continuously rotating the camera to keep our brains into a mode where we actually recognize it's a 3D image. Now the idea is if I just place this on my desktop or on my table next to my laptop, I actually have a full three-dimensional view of it, and it's live linked to whatever I'm doing on the laptop. So it gives me a peek into like a true 3D world, and I don't have to do these tricks with a rotating camera or anything. And I can also do these other visual gags like trails, so they can get more sense out of the actual motion that I'm using. And the nice thing here is that I still have all the control that I have on my regular 2D laptop. So I can use a mouse, I can use the touchpad, I can use the keyboard. I have all these, like literally hundreds of different widgets on the screen that I can manipulate, but at the same time I have a full 3D representation out of this. Now, I had that, and I also had another project coming up, which was a classic motion capture project, which they very creatively called Hololens. By then, the Hololens wasn't out yet when they started the project, so I want to show you a little clip of that, and at the same time explain what it is. So, Hololens was a European Union-funded project. It was done by a couple different companies, including the motion capture company I'm affiliated with. And the idea is, what if we combine really great dancers? So we had a flamenco dancer here. We had a couple different ballet dancers. We had old-style, like Greek traditional dance, and also very modern contemporary dance. And we're using this in our motion capture studio. So we had, I think, about 30 of these high-end Vicon cameras, which capture really minute detail. But we can also do live visualizations on that, which we usually already do for our own purposes. So we have it on the screen, but we also use it to see data quality, for example. And we had this HoloLens. So the idea was that maybe if we just do our regular shoots like we planned to, maybe in the last half a day or so, we have some playtime or in between takes, and we'll figure out what we can do. So here's the first section we did. So we went ahead and captured all our sequences. Now the goal here is to split this up into a database so that we can then run deep learning on it and to extract all these different motion clips out of it. But at the same time, we could do a live streaming thing again. So here's the live character being streamed to the HoloLens. So essentially, we do a live tracking of the markers, generate a skeleton out of that, and then using Motion Builder to retarget to the character and then stream it over Wi-Fi. And we can give it to a director. So here the director has a little Xbox controller, and he can do things like placement, but we can also switch visualizations for that, do all kinds of neat tricks. This actually shows the flaw of the Wi-Fi quite a bit. So we have quite a bit of latency, which was basically due to having a bad Wi-Fi router and already having some latency of the system. And the cool thing is, after the sequence, we could actually give the HoloLens to the performer, and it could actually, like within 20 seconds, they could walk around their own motion. And again, this is life size. That's exactly the same size as she is, which was an experience that they obviously didn't really have up to this point. So that was the first week. In the second week, we had the flamenco session. And usually in between takes, us, like the developers and the creatives, we have quite a bit of work to do, but in between we can play. So we did the whole week of captures for this. We captured a lot of like very long takes, which were very impressive, by the way. And then we started playing around more with different types of visualizations. Now, when we talk to these dancers, they're usually talking in very abstract concepts. So what I'm showing here, the first concept is called directionality. So the idea here is that we have these very simple arrows, but these dancers can figure out what the arrows do in relation to each other, and that's how they usually describe these concepts. Another one is called fluidity. So if we visualize it with these type of motion trails, they can very easily identify if there's any smooth lines or angular lines, for example. Now, we in the visual effects community, we still like to do virtual characters and even sets and props, because that allows us to visualize a lot of things. But part of this project is also to see what tools we can develop that can help dancers and choreographers to deal with this type of data in different or maybe new ways. And again, at the end of the session, we gave the HoloLens to Rosa here, and we noticed one peculiar thing. That was she was really focused. I mean, you can see here she's really focusing on a couple different things, and she asked us to do replays of takes, etc., and do slow motion stuff. So we asked her, we see that you're very focused and interested in this, but what is it that you see? And she told us, well, first of all, she is a dance teacher, and she told us that when she's looking at data like this, she's actually noticing a lot of things that she's doing wrong in her motion, that she's trying to convey her students not to do. But just the fact that she could walk around this, because I mean, she's very used to looking at a screen and looking at a mirror, or looking at her own performance. But the fact that she could now walk around it, and this was so precise, and it was actually in real space, that's somehow triggered her brain to deal with the data completely in a completely different way that she hadn't thought of before, at least hadn't seen before in that way. Anyway, so we've talked quite a bit on about the tools of today and tools of tomorrow, maybe, but I want to touch upon a little bit on the tools of next week, month, year, however far we want to look at. Now, one thing I identify, and we need designers and other people for this, I still see a lot of this happening. And what I mean with this is 2D interfaces that are floating in front of somebody. At the same time, we see all these Hollywood examples. Actually, I think most of these are real-world examples, where we still have 2D interfaces, but we also have three-dimensional elements. We're actually using this type of new technology to visualize three-dimensional data instead of having just panels for visualization. Here we have panels to have control, but the data is actually visualized in 3D. And I think we need more creatives that are coming from a design perspective to help a lot of the engineers that are more in a world where they're actually working with controls and widgets, but not really thinking in this new way. And the designer usually comes from the other side. I see that there's a perfect blend between the two. At the same time, from a visual effects standpoint, I'm also very excited about these type of devices, not so much these particular brands, because I mean, obviously it's a Magic Leap device, and it's an ODG, Austrian Design Group device. But the fact that this form factor is much smaller, which means that we can more easily distribute it on a live action or set, for example. And the idea is that we can have like a video village that streams out all these things to the actors, or at least with these devices, not to the actors, but to the directors, to the DOPs, director of photography, the cameraman, etc. And eventually we'll hopefully end up with things like this, and we can actually put in the eyes of the actors. Because if an actor can wear this while they're doing their thing in the motion or the performance capture studio, and they can look at the 3D character that the other person is playing, they can actually get the eye lines correct. We can get all the things in there from the set, from props. And the more we can get into context there, the fewer things we have to clean up in the end, we have to fiddle about with animation. And hopefully with this, all we have to do is do eye replacement in the end, which is very doable. But I think that's not even this year. That's a couple of years. That's a long time, unfortunately. But that's something we're looking forward to. But you know what? I think I've been rambling for quite a long time, so I'd like to thank you and open up the floor for questions if you have any. So.
Hello. Hi, Jasper. Greg
Hi.
Panos. The consumer level VR capture with devices like the Kinect and other things that are, some of which still available, some of which are evolving, like the Intel and being released continually. I've heard that a lot of them can only utilize like one machine per capture point. And where is this headed where you can buy multiple captures and then you can configure a typical machine for multiple points of view and share the data? Or I know like the Oculus Rift, you have 3 cameras and you saturate the USB bus on a pretty high-end computer. Well, what if you wanted to put even more cameras? Isn't there any way you can just dedicate a computer for the whole capture volume and then share all that information with all the users that want to inhabit that volume? And is that true also for 3D scanning and visual and depth-based acquisition of spaces as well.
That's a couple of questions in one, but you touch upon an interesting point, which is USB bandwidth, and that is the main limitation for especially the Kinect 2s and the Intel RealSense sensors, which are pretty much up to the spec level of what USB 3 bandwidth needs. So if you would put multiple on your machine, you have to start thinking about adding additional USB cards, which is definitely possible. And with Kinect 2, there's also a limitation in the SDK and the drivers. So for that reason, even if you pop multiple sensors on a machine that has enough bandwidth, you can't access them on a driver level. But it's very possible to use network machines and then stream data from multiple network machines, or at least have them all record in sync and then record it like that. Now, the example I showed with the multi-sensor body tracking, the beta application, that was done on a single machine. That was one Kinect 2 camera, two Kinect 1s, and two Orbex, I think. And that was for with an i7 desktop machine with a NVIDIA graphics card and some additional USB ports. So it's with these older style USB 2 cameras, it's fairly easy. With the newer style, you might need to network a few machines. But essentially, for body tracking, it's very light data to send it across the network, so you can then have one machine that does all the fusion, the skeleton fusion, so that one skeleton comes out of it. For point cloud stuff, that's usually a lot. It's either heavier on the network if you go uncompressed, or you have to compress quite a lot out of the data. So in that particular case, it's usually better to, if you're recording things and want to keep all the sensor data, it's better to do it on separate machines and just send like a single start and stop signal so that everything records in sync. That's usually how I do it. So.
Yeah, multi-capture, the multi-capture example that you were using, where there are lots of different cameras that self-calibrate or orient towards each other.
Yeah.
Are they using the projected dots or depth information in order to do that, or are they just using scene understanding of what's in the volume, using that as a reference?
Well, that's a proprietary technique for me, so I can't explain you all the magic details, but essentially it's using, for both the tracking and for the calibration, I'm using all the sensor data I have. So it's the raw infrared or color image, it's the depth image, and it's the skeleton tracking information I get. And even if there are different sensors, I can pick out the points that I need, and then I don't need like a full 30 frames a second point cloud for that. I just need different types of data.
Yeah. All right, thanks.
Welcome.
So at first I was like super excited when ARKit came out. Then after playing around with it, I was disappointed. So I felt it was like a step backwards from Tango. Like, to give you an example, and just actually this is a question, I'm wondering why. Like, for example, the Holo app, HOLI from 8i, their version of the Tango app is so much better than the one for iPhone X. For example, in the Tango app, you can have like multiple 3D characters in 3D space, right? On the iPhone X version, you can only have one character at a time. So why is it that? I mean, I have no idea, but why the step backwards?
I mean, I don't work for Google or Apple, so I don't know why they chose that. But I mean, it's I think it's a different objective that they're trying. I mean, for an AR application where you want to hold up your phone and project something into it, if you can do that on a phone that doesn't need specific sensors, that means you immediately have a much wider target audience. But as you say, and I think the previous question, the question also tapped into that, these depth sensors do give you a lot more info. So that actually the tracking might be more precise, but they also give you info on the surroundings, for example, which are very difficult, at least, to get from an RGB image. So there's definitely pros and cons, but I can see that for the main purpose of these things, for doing AR, phone-based AR, it makes sense to try and do it on as many phones as they can. And as it stands now, there aren't, besides the older Tango phones, there aren't many phones that have a depth sensor that's facing outward, which hopefully changes in the future. I don't know, but it's like...
Okay, so I have another question if no one else is gonna. So Shaquille O'Neal, the NBA player, he was on. Yeah. I guess he's the spokesperson for Magic Leap now or something at the Recode thing. So they're talking about like doing real-time mixed reality game streaming for NBA. Like they're on stage with the NBA commissioner. So of course with Magic Leap, right, they were super vague. They didn't explain like how they're doing it and everything. So like what do you think? How are they gonna? I mean, on the video they just showed like a 3D photogrammetry scan of Shaq, but then the CEO is talking about having like a tabletop NBA game live streamed in real time. Like, what's your like best guess about how they would actually do that? And I mean, the hint is in the videos they're showing like, it looks like just like a Vicon, like just white balls on Shaq or something. That's what he describes. They don't show it. And the other thing they're talking about is kind of forgot, but like, what do you think? How are they actually going to do that? Like, they're actually talking about they're not going to do the 3D scanning themselves. Or they actually want you to, as a developer, go to a 3D scanning shop. So It sounds like they're just going to use like standard tools. So what standard tools will allow you to like do a SIGGRAPH actually in 2016? I saw like Vicon doing like capture of like two basketball players on a half court. So it seemed pretty standard. But what do you think?
Well, there's obviously different solutions for that, and I don't know what Magic Leap is trying to promote here. But I mean, there's one fairly classic approach where you do motion capture, so you stick balls on people, or on an actor or a player like this, and then you recreate a character from scratch using that data, and that runs in any game engine, can be run on any mobile device. That's really quick. It's essentially what all games are doing. So that's one approach. And the other approach is actually volumetric video, which can either be depth sensors, or Intel showed some things with lots of regular cameras. Microsoft has this volumetric capture studio as well. And that's also very applicable to all these AR applications, whether it's AR on a mobile phone or in a headset or a VR headset, AR headset. And that obviously has the advantage that it's a video-based approach, so the likeness is there immediately. But the data for that is a bit heavier. So I don't know what Magic Leap is using in their specific example case, but it could match with both of these things. So. Next question.
Yeah, you described kind of a wide variety of sensors and tracking methods to determine depth. Could you talk a little bit about the Vive Pro and what's involved there, and what new possibilities that opens up, if any?
I don't think it's fundamentally different from, at least, I don't have one yet, so when I get back I should have one pretty soon. From what I understand, it's the hardware itself is more of a refined version, so I think that the mechanics are a bit simplified, so the production is easier and they might be more long-lasting. And I think from the software side, I think I heard hints that they can do multiple base stations. So currently it's 2 base stations, but I think they hinted at doing 4 of them with probably some different firmware. So that opens up, from my perspective, 2 possibilities. One is larger rooms, and the second one is you can potentially filter out occlusions. So for example, if my controller's here, then something at the back won't be able to see it. But if I have 4 different corners or up and down, then it might be able to solve occlusions like that. But I think they've definitely hinted at that, but I don't think that's ready yet. But that is definitely something I'm interested in, especially now that we have these tracker pods that we can stick on everything, and then occlusion becomes more of, not really an issue because it's very stable, but the more you can solve that, the better your data is going to be. So,
yeah. Look forward to that. Thanks.
Me too, actually. Okay, so I have time for one more question. Sorry.
So when it comes to the playback of the volumetric capture, like say using multiple sensors, it seems that right now they're all kind of inefficient file formats. You have FBX, OBJ sequences, or straight up point cloud data. So do you have a preferred playback to retain the image quality? And what do you think needs to kind of happen in that space? Like, do we need a new file format, or do we need better efficiency somewhere?
It's a very
Just
good
your
question.
thoughts, open-ended.
It's a very good question because, I mean, it is a lot of data. You can also store it in several ways. I mean, you can keep it as point cloud volumetric data, or you can do mesh-generated data. And also, there's a big difference if you're using it in a VR application, in real-time playback in a headset, for example, or like real-time playback in any engine, whatever device, versus playback in an animation pipeline, for example. So usually for animation pipelines, Alembic is a very widespread cache form. It's also an open source project by ILM and a couple of others. There's a GitHub page that it's basically all the 3D applications use that. I think Unreal also uses it. And that comes with very intelligent mesh compression algorithms that look at movement as well as vertex counts and if they change, for example, and as well as run length encoding, that kind of stuff. I think for pure volumetric, it's a lot trickier, and that can also tie into the rendering method. So like a point cloud rendering method you might prefer just like have a specific type of array in the right order and compressed in a certain way. But if you do array marching, like a true volumetric type of display, it triggers different things you want in the data format. So all those things make it very hard to come up with one standard that fits all. And I'm not actually aware if there are any projects like that. If somebody is aware, I would love to know, and I would love to learn about that. But I think we're still fairly early on in this technology, and everybody is using different ways to collect things. So and there's different endpoints, like I said. So I think that still needs to converge somewhat more in order to actually know what we need on a file format level. But
Cool, thank you.
okay, then I think that wraps it up. Thank you for coming.